So the goal today is to not only review power series, but to see how we can actually use power series to solve a differential equation, which is kind of terrifying at first if you think about it, because series were not something probably a lot of you, got really excited about. Unless you were in my Calc 2 class, then you found them incredibly exciting. But it's also not recent material. So the idea is that I can always solve a differential equation, but I might not be able to give you a closed form answer. And what that means is when you're evaluating an integral, right, you find an antiderivative. It's a closed form answer. You have a function, and now maybe you're evaluating that function. But if you were using, let's say, power series, Taylor polynomials, I can show you very simply that even if I can't do the integral, I can use the power series. And if I show it converges, then I can use something as simple as Wolfram. I did this in my class on Monday. Let's just add the first million terms, and I do it on Wolfram, and 1 second later I'm getting numerical values that are accurate to double-digit decimal places kind of stuff. The technology part's the easy stuff. It's determining when I can use it and how I use it in order to justify a final answer. But those are answers where the answer is not a closed form. Every problem we've solved so far, we were able to say y equals. Not y is approximately equal to some decimal. We say y equals this function or something to that nature. In this chapter, that's actually not our concern. If we can actually give a specific function, it's almost pure luck. It means that I actually recognize the form of a power series, and that's actually not entirely necessary. So let me do a really quick review of some of the stuff. So if I said I have this series, let's keep it really simple. I'll use I. So this is from I equal 1 to n, let's say, of ai. Okay, what does this mean? That means a1 plus a2, right, up to an. That's all it is. It's the summation notation. But I want to go over two very important properties of summations that we're going to use all the time. This, generally, the notation we use is S with a subscript of n, if you remember. It means the nth partial sum. A series is infinite. I always laugh when people say things like math, like, a straight line, as opposed to the other ones. Or every calculus book will refer to the infinite series. The word series means it is infinite. You can't have a finite series, but I can have a finite sum. That's called the nth partial sum, the sum of the first n terms of a series. Okay? A series automatically is infinite. But if I want to show you some algebraic manipulation, I need to do it on finite sums. And then what we do, remember, this is actually the easiest part of all. Because I can always take a limit, anything that I show for the finite sum I can then extend. So we're not doing two separate sets of rules. I would like to take that's just a different series, okay, or a different partial series. So b1 plus b2 up to bn. I want to add these together, all right? So that would mean I'm adding a1 plus a2 plus up to an, and I'm adding it to b1 plus b2 up to bn. Okay, great. But if the b's are either real numbers or functions, right? They're either scalars or scalar value functions, don't things like commutativity and associativity and things like that apply? Because I am just doing addition. So could I rewrite this as stare at that for a moment. Is that true?
Yes.
Those in discrete or have had discrete math, you do stuff like this all the time to manipulate. Yeah, that is absolutely true. But what's this? That's the sum from I equal 1 to n of ai plus bi. So this is the proof that the sum of the summations is the summation of the sums. Is that important? Yeah, we can't solve any problem using power series unless we can add power series and write them as one. That is one of our ultimate goals. Because you're going to have a sum of several different power series simultaneously, and we need to write it as one. So does it matter that that's an n? So if I went to infinity, it would still be true as long as they're both infinity. Now the second one, let's see. Limits, limit of a sum of the limits. Derivative of a sum of the derivatives. Integral of a sum of the integrals. Right? Linear transformation of a sum of the linear transformations. There's a whole bunch of things that are true for sums, and then there's one other thing that's always true also. Sums and what's the other thing we use? That is true with vectors, scalar multiples. That's the other thing. Think limits if it helps. So I have k times this. Well, that's k times a1 plus a2 plus an, but that's ka1 plus ka2 plus kan, but then that's the sum. So the scalar multiple can go in and out. Nothing with an index can go in and out, because the index is the thing that's changing. So that means, in simpler terms, if I take a linear combination of a summation, it's the summation of the linear combination. And by the way, that's one of the most important rules with linear transformations, right, from linear algebra, vectors and matrices and other things. But the sum and scalar multiple rules apply in most everything calc and above, we know that. But these are the things we're going to use basically to solve every problem, but you don't have to ask now, is that a legal move? You're going to actually just simply do it. So, does it ever get difficult? Well, I mean, it can, okay? Let's suppose, let me take just a random problem. Okay, here's a good one. So we have to see the big picture in a moment. Oops, sorry. I'll just write this one as 3an x to the n. All right. And this just looks horrible. And in a sense, it kind of is. My goal is to write one summation. There's a whole bunch of things wrong with this right now. Tell me something that is wrong with this right off the bat.
The indices do not match.
Yeah, I'm not starting at the same place. Okay. Well, that's easy enough to fix. I'm going to show you how to fix that. But if I'm not starting at the same place, can I just add them right now as one summation? No, I have to start at the same place. When I start with n equal 2, what's my first exponent?
X squared. Oh, x to the
It'll be x to the first power. And over here, it'll be x to the
0.
0th power. Ooh, they're not even the same degree. If it helps you sometimes, by the way, write out the first couple terms here. I get 2 times 3 times a2 x to the first plus 3 times 4 times a3 x to the second plus, okay? And then the second one is going to start off with what? Listen, it's going to be 3a0 x to the 0, and then plus 3a1 x to the first plus, and I got to add these together. Oh, man. Can I write just one happy power series that covers everything here? Not yet. So there's a couple things I need to do. One is I need them to start at the same place. That's actually an easy thing. And so I'm going to go through something that you hopefully did in Calc 2. Okay. All of the Taylor series that we used in Calc 2 are very relevant, and it's really important for everything we did in Calc 2. Remembering what the power series for e to the x, sine x, cos x, log x, inverse tan x, it's not that important. You're not going to use those results. Not on a regular basis. But I do want to remind you of something. We know that e to the x, this is the most important one of all. We know this. We derive it using the Taylor series. But I actually prove this before we get to the Taylor series. This will be one of the first things I do in my class on Monday in Calc 2. They just started power series today. Now, if I said write out the first few terms, often that's really useful. So the first term is going to be 1 over 1 x to the 0, so 1. And then it'll be 1 over 1 factorial, if you will, and then 1 over 2 factorial x squared, and 1 over 3 factorial x cubed, and okay. I'd like to take the derivative of this power series. I really can't differentiate the power series, but isn't the series a summation? And isn't the derivative of a sum, I said it, the sum of the derivatives? So what I like to do is, let's just write out the first few terms. Differentiate the first few terms. Oh, okay. Well, what will I get? Okay, 0, 1. I'll write it like that if you want. Or, sorry. And then this would be plus 1 over 2 factorial x squared. And then the next one would be 1 over 3 factorial x. Oh. What do I notice?
It's the same.
Exact same terms, forever and ever and ever and ever. Ooh. Now, what's the nth term here? This is the key part. This is how I can save myself. I don't want to do this. It takes too long. The nth term is this. And then the very next term would be, just for fun, so if I differentiate this term, what do I get? I get 1 over n minus 1 factorial x to the n minus 1. I know when I differentiate this term, I'm going to get that. But let's say I stopped here. Then everything I said here is absolutely true. This is the first, here, this is the first n plus 1 terms, because the first term is a constant. So I went to the n. Now, I took the derivative of every one of those terms, and I'm now here. Can I write this as a power series? Yeah. It would be the sum from n equals something to something, 1 over something factorial, x to the something. Can't start at 0.
You start at 1.
Because I can't have a negative number factorial, but it would start at 1, wouldn't it? Oh, okay. Now then I would have n minus 1 factorial. Now, okay. Everybody okay with that? But I'd really like it to start at 0. And that's the key. That's the step you're going to do the most often. Is everybody okay with what I just wrote there? That is the last term I have, but it has to start at 1. But I want it to start at 0. Well, let's see. When I start at 1, my first term is going to be 0 factorial. And my first exponent is going to be x to the 0. So if I start at 0, then won't that be that? When you shift it to change your starting point, whether you shift it 1, 2, 5, 10, 1,000 units, you're just going to shift the end. You just have to know you're going in the right direction. And the way I do it is, okay, my first term is going to be 1 over 0 factorial x to the 0. So when I start at 0, I'm 1 over 0 factorial. Okay, I went in the right direction. See, if I made it n minus 2, that'd been the wrong direction. I'm only moving 1 unit, and it's not like there's a lot of choices, right? Forward or backward. See, you all with me? This is one of the most common steps. So what did I just prove? I just proved the derivative of that power series is equal to itself. What's the only function that equals its own derivative? E to the x. And if we integrate it, we get the same result. That's actually the formal proof of where it comes from before you did the Taylor series, which is now you got to do a whole bunch of derivatives, evaluate all your derivatives, come up with the general terms. It's a lot more work. This is kind of cool. But the point is this is what I'm going to do in my Calc 2 to show them how to shift the index. I cannot add these unless they start at the same place. Where do they both need to start?
0 or 1.
This one can't start at 0, can it?
No.
Not if I want it just to be x to the n. Let's say I want it to be x to the n. Now, if I start at 0, then I'd have x to the n plus 1, but then that won't work for this one. So I would like to start at 0. No, probably have to start at 1. So let's go to the first one. If I start that one at 1, I'm shifting it exactly 1 unit. I'm going to have something, something, a with a something, and an x to the something. How's that? Okay, what is my first term right now? 2 times 3. So if I start at 1, how am I going to get a 2?
N plus 1.
And plus 1. How am I going to get a 3? And plus 2. I shifted 1 unit. That actually should be this easy. A 2
N plus 1.
and plus 1. X to the first power.
Next to the n.
Are we good? So now, wait, I don't have to do hardly anything to this one. It's already next to the n. except they don't start at the same place. Okay. We've done this with factorials before, and it's really the same concept. I have to remind people all the time. I would like you to do this without a calculator. So you don't want to calculate 10 factorial, calculate 8 factorial, and then do the long division by hand. So what are you going to do? I say you're going to run off the first few terms. You're going to run off the first few terms. I need to run off that term, because then they will start at the same place. So this guy here, so this is my answer so far. It's this plus this. So what's this? Well, when n is 0, what do I get?
3, 8, 0.
Nothing changes, because I just told you what the first term was. Now it's going to start at 1. And now I'm going to add that. Dittos, I'm going to be lazy. I'm going to add to that. Can I now add these together?
Yes.
They start at the same place, and they have the same exponent on the end. That is when I can add them. I cannot add them one step before then. Now, you've never done this before when you've done power series, because you never had cause to add two power series together. We're always going to be adding power series together now. So, give me a bestest, mostest, correctest-ish final answer.
3, 8, 0.
Good. And by the way, I don't need to include that in the power series because I can't. It would not be possible to include that as part of the power series. That's just my constant up front. So now, big brackets. It does not matter which one I write. I'll do that one first.
That's 3 equal to 3a. So,
That's 3an. And it's all times x to the n. I don't want to write x to the n twice. There's no benefit. Because now, whatever this is, I can tell you what every term is going to be. My n is 1, 2, 3, 4, 5, and so on. Now, one of our goals later on is to figure out the a's. Okay, and that's not a trivial thing. What if I said to you, here's my original statement of the problem, and I would like all of this to equal, I don't know, 0. Does that mean that all my a's are 0? No, it means the whole thing adds to 0. It's not the same thing, is it? But what that would therefore mean is that all of these would have to equal 0. And now I would have a simple way of relating the n plus first value to the nth value. It would actually give me a formula, an algorithm to find the coefficients. You guys did something in a much lower version on the quiz you just turned in, didn't you? Didn't you solve the differential equation? You set it equal to 0, and then you had your C1s and C2s, and you equated them, and that's how you figured out when they were equal or opposite signs? You didn't tell me the C's were 0, because they're not. They could be any real number. Oh, it's just the other one was the same value, or it was the opposite sign, I think. Is that correct?
Yeah.
On all of them. It was the sum that was 0, not the individual. So what we're going to be doing in general is doing things like this, where this sum is. Now, I don't care what, I'm not looking for an answer to this problem. I'm showing you the algebra along the way. So let's suppose I needed to know where this is 0. So this is what we then do. We'd say n plus 1 times n plus 2 times an plus 1 is equal to the negative of 3an. And you always solve for the higher number. So therefore, the n plus first term would be negative 3 times the nth term. This would be the governing formula that relates my coefficients of whatever my final answer is going to be. Don't even worry about that. We'll get to it. So what I would do is I'd say, okay, when a is 0, what do I get for a1? Then when a1, what do I get for a2? And so on. And what am I looking for? Think Calc 2. I'm looking for a pattern. Is there always going to be a clear, recognizable pattern? No. In Calc 2, yeah, there always was. In Calc 1, every integral that ever showed up in every Calc 1 class in the history of Calc 1, you could find in Calc 1, using Calc 1 techniques. Not so much in Calc 2 because you needed other things. So every series, you could always find the coefficients in Calc 2, but in reality, no, most of the time you probably can't. But our goal is always to locate a pattern. And if you remember, most of the patterns were either exponential or factorial. And we're going to do a few examples. If I see a clear pattern, then it makes it really easy to say an plus 1 is this. If I don't, I have to do other things that are not as pleasant. So make a question.
Yeah, so like, if that whole equation there equals 0, and we determine that all of that is what's on the left side of that equation there, how come, like what happened to the 3a naught?
Oh, no, we're not actually interested in the solution to this problem. I'm just saying this is something you're going to do in general.
Oh, okay.
So that means that this would be 0 also, and so on and so on. But what you'd be doing, you're saying, I have to set all my coefficients equal to 0. Now, when you're setting your coefficients, you're saying, I'm setting this sum equal to 0. I'm not setting every individual coefficient equal to 0. Because if that were the case, it'd be kind of a boring function. Right? Everything's 0. So this is all kind of new unexplored territory. Now, I don't need you to remember really much of anything about the stuff you did in Calc 2. But there are certain things that you had to be able to remember, like, things like interval of convergence and stuff like that. We love it when things converge over the entire number line, but they usually don't. It's usually going to be a more narrow interval. But exponential signs and cosines always did converge over the whole number line. So I'm going to walk you through a process. I could care less about the final answer. Final answer is whatever the final answer is. Think about every problem we've done. Is the final answer the most important part? No, it's the process you use to figure it out. And every time we change a problem, you got used to the processes. And then you got different answers, but you always got the process correct. You just did Cauchy-Euler recently, right? You've done variation parameters recently. Which reminds me, on the last quiz, it was very interesting. About half of you did the non-homogeneous problem. About half of you used variation parameters. And by the way, you did a really good job in general. And about half of you used method of undetermined coefficients. Problem is, that one gave us more problem because we forgot. You got an x cubed, method of undetermined coefficients, you kind of have to have an x squared and an x and a constant, and not all of those were 0, by the way. So those who did variation, it was more work. But you pretty much were all correct. Those who did the other one, everybody just did an x cubed and it worked. It worked, but it kind of fudged it a little bit. Yeah, it's kind of like when there's a sine and a cosine and you only put the sine. It's probably not going to work, but I could get lucky and it worked on that problem. But I probably need both the sine and the cosine. Yeah, so just don't forget when you're doing undetermined coefficients and it's polynomial, you need degrees all the way down. Now, it turns out you got kind of lucky because some of the coefficients were 0 and one of them could be any real number, but it ended up being of the linear term, and that was already a solution to the homogeneous, so you would have just added that coefficient. So it all worked out in the end. Everybody understand it? It was kind of an interesting problem because I wanted to see what you guys did. And I think you asked me, and I said, well, you did variation correctly. And I said, the other one's actually less algebra. That was wink, wink. You had to do it, set it up correctly. So the variation people, that was absolutely correct. It was a lot more work, but we pretty much, I think it was pretty close to 100%. The other one, it wasn't that you did it wrong. It's that leaving something out, it was more lucky that it worked than skill. So let's solve the following problem. I want to keep this really simple, okay? Now we're going to do this using a power series, and I'm going to show you every step of the way because the complexity is going to grow over the next couple days, but the process will always start the same. So we start by saying, okay, let me go backwards a little bit. There's an upper division math course that some of you may take if you're math majors called functional analysis. It's a very powerful course. The concept here is that any function that exists, every function exists, whether it's transcendental, sines, cosines, e to the x's, or algebraic, or I think polynomials or square roots of polynomials. Every single function that exists is equal to a polynomial. E to the x, I just wrote e to the x. It's equal to a polynomial. Oh, by the way, what's the degree?
Infinite.
Infinite. So in other words, every function that exists is equal to a power series. If I just randomly wrote a power series on the board, it isn't equal to any specific function. I just made it up. No, it's in reverse. Every function that exists, there is a specific power series that's equal to it. There are a lot more power series than functions that would map to them. So if you just randomly made up a power series, no, there's no function probably that is equal to that you can, oh, that's e to the x, that's sine x. No, but if I have e to the x or sine x or tan x or inverse tan x or log x, there is a very specific power series, and we called it a Taylor series because of how we found it. That was the specific way of doing the derivatives. But the point being, if every function that exists is equal to a power series at some point, then why did we learn them? Because if I wanted to do something, I want to do this. Okay. Oh, I'll just say 0.5. Okay, something simple. Okay, yeah, like that's really hard. Great. Now, I want to do, this. Yeah, unless f of x is a scalar multiple of x, of the infinitely many things that go there, guess what? None of them have antiderivatives. Can't do any of them. Almost every function you know of, if you replace the x with a function of x, it can't be done. Occasionally I get lucky. Maybe I have some clever substitution. If I decide to replace f of x with, I don't know, log x, e to the x, square root of x, it probably has no antiderivative. But if I replace the sine function with its power series, now I'm integrating polynomial. I spend a lot of time in my calc doing this. This is probably the thing we spend the most time with. I call it the impossible problem. We will look at impossible problems and then we will answer them. Problems that cannot be done even using any form of technology. Why? Because there's no antiderivative, but we still want a value. But we're giving a numerical value. We're not giving a function. So we do the power series, and then we show if the power series converges, the terms get really small really fast. I did a number of seminars a few years ago. We had a whole series of STEM lectures. And one of the ones I did was based on this. I would do these problems. I'd write the first 4 terms of the Taylor series, and then I would show you that we'd get convergence to like 14 decimal places. I can get convergence past what a calculator will show you on the screen, usually just 3 or 4 terms if you're doing it right. It's not complicated. So when the computer's giving you that numerical answer, it's doing the same thing, just doing it faster than I can plug the buttons in. If a series converges, it means the terms are getting so small, so fast, that the next term changes further out in the decimal. The next term's further still. So I might change the 2nd decimal place, then the 5th, then the 9th, then the 15th. And in a very short amount of time, you've got as many decimals as you need. So I can absolutely guarantee you, I can give you as many decimal places as you need. I need 100 decimal place accuracy. Okay, I can guarantee it. I just have to do a few more terms, maybe. But you can always do this no matter what the question is if the series converges. That's why you spent so much time in Calc 2 figuring out how to prove convergence. Then you only looked at things that converge. You don't care about the ones that diverge. So part of the reason we learned the power series is so I can do problems that otherwise could not necessarily be done. And if I can do that, it opens up the door. So based on what I just said, I don't know what the answer to this question is. Actually, we do. But let's pretend like we have no idea what the answer to this question is. But we can absolutely say, if this question has a function that's an answer, that function is absolutely equal to a power series. So I'm going to say, let's let y equal. Now, the formal definition of a power series, lest we forget, the formal definition is anything that is in this form. We say this is expanded about C. And if you remember how you derived it, the Taylor series was you took derivatives of f of x, and then you evaluated them at C, and the coefficient was now f prime or f double prime or f triple prime divided by the appropriate factorial. So in other words, the nth derivative evaluated at C divided by n factorial. This is every function that exists follows this rule. This is what we prove when we do Taylor series. But then I always point out in my calc classes, that's the general term. What is C usually? 0, and the rest of the time, 1. It's 0 unless your derivatives don't exist at 0. For example, the natural log. Oh, okay, none of my derivatives exist at 0, so I got to do it at 1. That's it. Anything where the derivatives don't exist at 0, it's 1. Now, there's a term there that you guys should have learned, and I use this even in my lower level calculus classes, the term analytic. And we're going to use that a lot in the upcoming future. How many have heard that term in a math context? Do you remember what it means?
Does it mean that the function is differentiable everything?
It means, well, flip it. It's everywhere the function is differentiable. So if I'm analytic for all real numbers and the function is differentiable for all real numbers, all polynomials, or sine and cosine, e to the x. what about something like the square root function? It's not differentiable at 0, and in fact, every derivative after that, 0 is in the ooh. So it's only analytic for positive numbers. So analytic is everywhere the derivative exists. Oh, okay. So if I have a function and the function and all of its derivatives exist at 0, then I'm using 0. It's so much easier. But what if they don't? Like the natural log function? Okay, then we're going to use 1. And by the way, I've never seen an example of any other numbers ever used because there's no benefit. So what we're going to do is we're going to say, no, we're going to make this simple. I don't have anything in front, which automatically means this thing's going to be defined as 0. If I have an x in front, remember 0 is the problem because we'd be dividing through by x. We're not doing that problem. We're doing something where there's not an x in front. I can have an x here. That's not a problem. I'm just not going to start with an x there. So what we're going to do, we're going to make it easier on ourselves. We're going to do this. Because that's easier. Does everybody agree? It's not more right or less right. It's just easier to work with overall. I could still expand about a different number, but there's no advantage gained. So I need two derivatives. And here's the beautiful thing, based on what I showed you earlier. I just need to differentiate that. Oh, okay, so what's the derivative of this? It's n, a n,
X.
n minus 1, but where must it now start?
That's 1.
It's got to start at 1 for two reasons. One is I can't have a negative exponent. But also, if I started at 0, it would be the first term of my power series is a 0. And that's one of the rules about a power series. The first term cannot be 0. I can get zeros down the road. But a power series has got to start with a non-zero, and I can't have anything be undefined. That also is a problem. Okay, so this has to start at 1. And if I had expanded this and then said, let's all take the first derivative, they would all look like this, wouldn't they? Agreed? So what's the second derivative? So n minus 1, a n, x to the n minus 2, and this will start at 2. Every problem we attempt over the next week or two is going to start with this. Well, most of the problems. We're going to learn different forms of tweakages as they become necessary. So let's take that and substitute it into there. I want the process to be simple. When it comes to looking for patterns and things, that's a completely separate animal. We'll discuss. That's not an issue. Nope. I don't need anyone here to be able to see patterns. I just need you to be able to set things up correctly. If patterns emerge that are clear, identifiable, you're all going to come up with the same answers. If they're not clear and easily identifiable, then it doesn't matter. You should never have to be clever in order to answer the question. So let's start with this. Is that right?
Yes.
Okay. I would really like to write this as one power series, and this one's not going to be that hard.
We have to subtract 1 from that n. And add
Should
1.
I tweak the one on the right or the one on the left?
On the
The
right.
one to the right.
By the way, both, yes for both, but
Yeah.
I think I would rather go 0 and n,
Yeah.
because what's my first term here going to be? Isn't it going to be x to the 0?
Oh, that's true.
Okay, little drum roll, please. First of all, is that correct?
Yes.
So I shifted it in the right direction. I just shifted it 2 units. I only have 2 choices. It's either n minus 4 or it's n. Everybody understand there's not another option. So what are these numbers? Well, let's see. I need to get 2 times 1, but I'm starting with a 0. So how do I get 2?
N plus.
n plus 2. How do I get a 1?
N
n plus 1.
A n plus 2.
Yeah. N plus 2.
n plus 2. I want that to be the easiest part of the problem every time. There's nothing I did there that was complicated. I shifted the starting point 2 units. And how do I know if I went in the right direction? Easy. I need my first term to be 2 times 1 times A2. It's now 2 times 1 times A2. Okay, I went in the right direction. That's it. It has to be that simple every time. Yeah, Patrick.
No, I got you. You just added 2 to the ends. and
Okay,
power.
now, do I need to do anything to the second one?
No, I don't think so.
Life is good.
Is that 4 just a constant? That's
Yes.
all that? We don't need to worry about it?
I'm sorry?
We just don't need to worry about it?
Well, we're gonna use it in a moment, but it's, could I put it on the inside?
Yeah.
Yeah, we're going to. I don't have to have it on the inside yet. When I make one power series, yes, then it has to be on the inside. Can I now write this as one big happy power series?
Yes.
Because both of them start at 0 and both of them have x to the n. Both things have to be true. Okay? I don't have to start at 0. I just like starting at 0. That makes, makes me happy. So, what do I got? I got n plus 2, n plus 1, a n plus 2, minus 4an. So now you got your 4 on the inside. It didn't matter when I put it in, but I have to put it in by now. Oh, and by the way, what does all of this have to equal?
0.
0. You aren't going to do anything other than homogeneous. We don't have the means. Because I have a power series on the left, it is a polynomial. I can't have a trig function on the right. That wouldn't work. Right? No, power series only works for the homogeneous series. And I don't have to have constant coefficients, by the way. I can have variables. That's not a problem. But I can't have things like square roots. Oh, so I can have x's to powers. That won't be a problem. So it'll look a lot more like Cauchy-Euler kind of things. Except the difference was in Cauchy-Euler, the exponents were limited, weren't they? It was x squared on the second derivative, x to the first on the first derivative, constant on the function. That was very specific for Cauchy-Euler. Could we tweak it? Yeah, but as long as I kept the degree difference, right? 210, 321, 4, I could do that. That would still work. We just didn't do any of those. Now, what is the next thing, you suppose?
Set the inside equal to 0.
I want this part here to equal 0. So I'm going to write n plus 2 times n plus 1 times a n plus 2 has to now equal 4an. Therefore, a n plus 2 has to equal 4 over n plus 2 n plus 1. I like leaving the an out of the quotient. I find it just easier to manipulate and interpret. So, one of two things. I'm going to run off several coefficients, and I will either see a clear recognizable pattern or I won't. And I don't care. If I see a clear recognizable pattern, I will take every advantage of it because it makes my final answer a lot easier to state. If I don't, then I'm going to have the ugliest form of the final answer, in which case you have a bunch of terms and a plus dot dot dot. Which, if you go back to your Calc 2 book, was the answer to almost every question asked, even when there was a closed form, because not one calculus author, and I have about 25 different books, and I've helped these people, and it's like, guys, every problem you put a plus dot 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 had a closed form, but I don't know how to do it, because they didn't know how to manipulate. There are some really simple manipulations of odd and even coefficients and factorials and stuff, and I show my Calc 2 class that they're not that complicated. So in the textbooks, they never give closed forms of an answer. They give a bunch of terms plus dot dot dot. Well, unfortunately, that's going to be the nature of probably most of our answers. So I said, don't worry about it. If you see a pattern, rejoice. If you don't sweat it. Why? Because once you are this far, could you do a do loop and have a computer generate the first, 1,000 coefficients? Do you understand that you can always do things like that? That won't help me find a pattern. That's what I would do if I don't see a pattern. Now, let's write down a couple things. So, my very, 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 very first smallest term is going to be an A0. Agreed? So let's start with n equals 0. And just put in parentheses, this is obviously n is greater than or equal to 0. So A2, that means n is 0, is what? 4 over 2 times 1 times A0, or 2A0. Okay, great. Now, A3 is not going to involve either one of these two. A3 is going to involve A1, isn't it? But then A4 is going to involve A2 again. Do you notice something? I'm going to have odd and I'm going to have even, and I probably would be better off keeping them separate. Because I can't see a pattern of odds to evens, but I can see a pattern of odds to odds. So over here, what's A3? That means n equals 1.
4 over 6.
Well, I'll write it 4 over 3 times 2
Yeah.
times A1. Now come back to here. What's A4? By the way, if these only differed by 1, then you would just write all of them at one time, because each one would refer to the previous one. But these skip 2 at a time. That's why I'm keeping them separate. So what's A4? That would be 4 over, that means n is 2. 4 over 4 times 3 times A2. In fact, what if I just leave it like that? Wouldn't that then be 4 squared over 4 times 3 times 2 times 1 times A0? Sometimes it's better not to simplify, by the way. Does everyone see that?
Yeah.
Just for fun, just to make sure we actually are seeing what we see. What's A6? That means n is 4.
Yeah. 4 over 8 times.
4 over
Oh, yeah.
6 times 5 times A4. But that would be 4 cubed over 6 times 5 times 4 times 3 times 2 times 1 times A0. And he thinks he sees a pattern right now. I said before, when patterns exist, I said they are usually one of 2 things. Do you remember what I said? Exponential or factorial. This happens to be both. Do we see a pattern here for the evens? How do I say it then? I don't say AN, because N is neither odd nor even.
N plus 2.
I'd say A2N.
4 to the n.
Right now, 2N. So this is 2 times 3. This is 2 times 2. This is 2 times 1. So this is 2 times N. That was 2 times 3. Do you notice? 4 to the n. Good.
2n factorial. Yeah.
2n factorial. We lucked out. You cannot guarantee this is going to happen. In fact, I'm telling you right now, most of the time it's probably not going to happen. But when it does, you want to jump on it because it's right there. I can show you how to look for patterns. Exponential patterns are easy. You say 4, then 4 squared, then 4 cubed, then 4. Pretty sure I see that pattern. But if I had simplified each of these as I went, then this would have been 2 and this would have been 2/3, and then I don't think I would have seen anything. Do you understand what I'm saying? So sometimes maybe don't simplify right away. I cannot teach you how to see patterns. That is not something that can be taught. That's actually something you're literally born with. To recognize clear and obvious ones, because when you did series, you remember doing things like geometric series. Very important, and they're really easy to identify. Arithmetic, that's where I'm counting by the same number. Easy to identify. In some cases, you had recursive ones. Those are trickier, like the Fibonacci numbers, things like that. You see certain patterns, but they were usually really low level. The ability to see patterns, especially when other people can't, that's actually a gift. That cannot be taught. It's what to do with those patterns. There's a branch, it's not mathematics, it'd be more computer programming that deals with the ability to see patterns. Do we know what that is called? I'll give you a hint. Any hackers here? Be honest. Any hackers here?
Oh, yeah.
Any hackers here? So I know people that are hackers. Usually make the best programmers. Usually the ones that companies want to hire, because you know how to get through their firewall. And if you know how to get to their firewall, then what can you do? Help them
Build a bigger.
build a better firewall. In other words, you can't have a better firewall until you know how the previous one was hacked. So the hackers, also called the code breakers, that's an entire branch of mathematics called cryptography, code breaking. And it was dormant for most of the 20th century because there wasn't a whole lot of use of it after World War II. How many have seen A Beautiful Mind? Incredible movie, true story, based on a true story, right? John Nash. John Nash was one of the smartest guys that lived last century. Okay, if you haven't seen the movie, you should see it. Russell Crowe plays John Nash. He's a tortured genius. And during World War II, he helped break the Nazis' codes. And there's a scene in the movie that's just, to me, mind-blowing. He's in a room, huge wall, literally thousands of symbols on the wall. Letters, numbers, Greek letters, just symbols that were complete random gibberish. The US government had intercepted these. And he's looking at it, but he sees symbols in his brain. He sees symbols coming out of the wall, and he's deconstructing it and breaking the code. No human who had ever lived was capable of doing this, quite literally. And because of that and his super genius, we were able to break a lot of the Nazi codes. Now, what's really crazy is there's another movie that came out several years later with Benedict Cumberbatch. The name's always escaping me. Imitation Game. He's basically the same guy, but over in England. And he's doing the exact same thing. He's breaking the Nazi codes. He's the one that solves the Enigma machine, which was a very, very big deal. Same kind of thing. These were both very, very tortured geniuses. John Nash's story is very interesting because if you watch the movie, you know, his best friend, who's Paul Bettany, I think is the actor. His best friend all through school and life, and he finds out later.
Imaginary.
Yeah, it doesn't actually exist because he's severely schizophrenic. Yeah, like I say, it's an incredible movie. One of the smartest people to live in the 20th century was also schizophrenic and tortured, but his gift was being able to see patterns that nobody else could see. You can't teach that, but if you have that ability, oh my goodness, are you a valuable asset to any, major computer company, especially ones who are trying to do security. You can't be good at doing this unless you know how to break stuff. And I say this sort of jokingly. Some of you have had me for Calc 3 or even linear algebra. I tell people all the time, you have to find ways, I always say, to screw up the technology. You have to find problems the technology can't answer. You have to find ways to ask a question where your calculator or your computer can't answer it. Because when you can do that, then you can automatically start making a better one. When I was a grad student at UCSD, one of the projects we always had was, I remember this, it was really simple, come up with a simple system of equations that the supercomputer at UCSD couldn't solve. And I came up with a really easy one. The key was using the number 803 as a coefficient, because 803, I knew at the time, has as a fraction, as a denominator, is one of the longest known sequences before it repeats. It's like more than 100 digits. And there is no technology on planet Earth that would store that many. So I would come up with a simple equation where I would give you, it'd be like, 802x plus x equals 803. 1 comma 1 was the solution. I'd ask a couple of questions where I'd use this. And then we'd feed it into the computer, and the answer was 1, 1, and I would do it by hand in 30 seconds. The computer would spit out numbers where the ordered pair was in the thousands, if not millions. It's called an ill-conditioned matrix because of round-off errors, because computers can't store fractions. You guys, anybody's programmed this, it's a real number or it's an integer. So the first step in any computer when solving a matrix problem is to make a lead coefficient of 1. But if your lead coefficient is 803, 803x minus 802y equals 1, it's now putting and storing decimals, but it's rounding those decimals off automatically to whatever. It's the point being, if you know how to ask the question that will screw up the technology, then you can immediately start improving the technology. The early days of the calculators, the TIs, maybe the worst technology in the history of technology. The TI 81s and 82s were so bad, I'd have students bring them to class. A graphing calculator that graphed nothing to the left of the y-axis, it wouldn't accept negative input, it would tell you an error. When you wanted to square -1, it would say error. It was a pretty major screw up. And those calculators, when they came out in the early 1980s, were more than the cost of a car, no joke. The calculator cost more than a car. And they were awful, but because they discovered the errors. I'm that person, I never buy new technology. Nope, I'm gonna wait till the 3rd or 4th generation. I'm still waiting for the electric vehicle that goes 500 miles, then I'll consider it. Why? Because the first generation is always terrible. But the second generation is infinitely better, but the third is only usually a little bit better, the fourth is maybe barely better, because we're fixing the bugs. That's what you guys are gonna do. You're gonna stand on the shoulders of the people that came before you. But if you have certain abilities, if you can recognize certain patterns, you have an edge that other people don't have. Now, that doesn't mean automatically you're gonna be over and above everybody else, but it means you'll be able to answer questions that other people may not be able to answer. I saw a clear pattern here, I'm gonna take advantage of it. Does that guarantee there's a pattern for the odds?
Maybe not.
No, but
Probably.
there probably is, good. And by the way, it's not hard for me to come up with a problem where one of them is really easy and the other one I can't see it at all. It really isn't that hard to come up with problems that aren't clean. So, do we all agree that that is clearly the coefficient for the even terms?
Would we have to add a to the 0 to that?
Oh, I'm sorry, thank you, Lee. Yes, sorry.
Yeah.
Yeah, there's gotta be an A0 there. And by the way, if I don't have an initial condition, then A0 just makes its way to my final answer. If I gave you an initial condition, then you'd have a value for A0. So don't sweat that at all. I'll walk you through that part too. Now, how about here? What's A5? Well,
4.
that means N is 3, so
the
it's 4 over
5 times 4.
5 times 4 times
A3.
A3, but that would be 4 squared. 5, 4, 3, 2. You don't think, do you? So this would be 4 over 7 times 6, A5, which would be 4 cubed. 7, oh, I think I see it. By the way, but I don't have a 1 there. Do I need a 1 to make this a factorial?
No.
No, so there's clearly a factorial here. A2n,
Plus 1.
should I go plus 1 or minus 1?
Plus 1.
Plus
Plus 1 because we said n was starting at 0. That is important. And by the way, there would be nothing wrong with you saying minus 1, but it makes the recursion here a little bit trickier. Okay. So on A7, n was 3. On A5, n was 2. Is that a good thing?
Yes.
Yeah. So this is still that. And my factorial?
2n plus 1.
1.
Factorial.
Oh, I'm liking this a lot. You guys digging on this so far?
Mhm.
Now, what would really be cool is if these were the same number. But I'm not worried about that. So now I'm going to answer the question. At least I'm going to give the first iteration of the answer. So it appears to me that y is going to equal. Now, don't write this out, but the form of my answer is, right, a0 plus a1x plus a2x squared. This is the form of the answer. Do you really want to write all of these coefficients out? No, but the evens and the odds are clearly separate, aren't they? So could I write it as a sum of the even terms and add it to the sum of the odd terms?
Yes.
Does everybody understand that if you don't see a pattern, then you're actually writing your answer like this? You're putting as many terms as you figured out, and then you're putting plus dot dot dot, because that's the best you can possibly do. But you saw a pattern. And so if I said the answer is A0 plus A1x plus, and now I go to here and say this A0x squared, and then this A1x cubed, and then this A, does everybody understand? I could do that forever and ever. But separating means I can write a summation cleaner. So, what are the evens? I'll write it out. It's A0 plus A2x squared plus A4x to the 4th plus, these are the evens. I'm going to erase this because I don't need this right now. And then the odds would be plus A1x plus A3x cubed plus A5x to the 5th plus dot dot dot. Okay. So since A2, A4, and every even A after that can actually be written as something times A0. Everybody see that?
Yeah.
Look at the far right. Then can I simply say this is going to be nothing more than A0 times,
1 plus.
but I want to write it like this. What am I going to write there?
That
Oh,
thing.
4n over 2n factorial.
But I already pulled the A0 out in front, didn't I? So how about 4 to the n over 2n factorial x to what power?
To the n, 2n.
Sorry, I got over that. X to the 2n, because those were the evens. And check, my first one's going to be x to the 0, the next squared, the next 4th. like that says there. Okay? Plus A1 times. You are very happy if you could write something in this form. You are very happy. So we got too much stuff here. All right. So what's going to go here? Well, basically that. So I'm going to have 4 to the n, 2n plus 1 factorial, x to the 2n plus 1. Can I possibly put these two together?
No.
There would be absolutely no advantage whatsoever. I would lose a lot of information. So everything we have is cool, everything we have is beautiful. I was able to write closed forms of my answer. I am happy, I am walking away. But I've got this itch that just, God, I feel like I should be able to go further. I feel like I should know the answer to this question. And I'm saying, no, I'm really happy if you got this far. But can we go further?
Yes.
Yeah, actually we can. And I'm gonna show you, sometimes you get lucky. And I did give you a hint. Isn't 4 2 squared? Isn't that true? So could I have written that as 2 to the 2n? Now, by the way, 2 to the 2n is not somehow superior to 4 to the n. But it means that the indices are now exactly the same. Everybody see that?
Yeah.
But I can't possibly do that on the next one, can I? I don't know. Let me erase this stuff. So the other one, this is an equal, sorry. Could I write 2 squared to the n over 2n plus 1 factorial a1? Could I do that?
Yes.
The problem is it's not gonna be exactly what I want. If only I had another 2. Oh my gosh, everybody look, it's Elvis. Oh, never mind, it was Professor Mona, I was kidding. Oh, look, I have it too. Can I just do that?
You have to divide.
Ooh. Now what have I got?
2n plus 1 over 2.
Huh. Huh. Is that legal?
Yeah.
We did, it must be legal. We would never do anything we can't do, right? That would be wrong. So I just rewrote this as A0 2 to the 2n over 2n factorial x to the 2n. And then what was it? Plus 1/2 a1. Do I have everything that I need? 2 to the 2n plus 1? Make sure I got that correct. Yeah. Over 2n plus 1. I think I got that right, didn't I? We don't have it. I'm just making sure we don't have any boo-boos anywhere. I think that's right. That's loud. Is that a better answer or just a different answer?
Just
A different answer.
But there are times when that different answer may actually be very, very useful. I don't need to do things. I want you to be able to manipulate. If you saw a pattern, rejoice. You might not see a pattern. Most of the time, there's no pattern. So what if there's no pattern? Let's just change one thing. You know, what if that was, I don't know, n plus 5, whatever. You're going to write the first few terms, And by the way, if you're not seeing a pattern, you're probably now simplifying the fractions. Because you don't want gargantuan numerator and denominator. You're probably going 3 or 4 terms on each side, and then you're writing your answer as the first several terms plus dot, dot, dot. But the key was, once you came up with this formula, that's where you can use the technology and do your do loop to find your other coefficients. Okay? Most of the time, you cannot write your answer in a closed form. We can live with that. Yeah.
This newest step that we got to here, to the left.
This
Yeah,
one?
here. Now they're starting to look like if you called it to n, let's just say another variable m, right? We have like x to the m over m factorial.
Well, not exact, because you are skipping numbers, but I know what you're saying.
Like, do we have problems where we replace the whole series with the function that they're equal to, possibly?
If you saw it, but that means you'd have to remember them all. And it's, most of the time, you're not going to. A lot of times, there will be problems where you actually see a clear identifiable pattern of the coefficients, but it still doesn't translate into a specific function that you might recognize. And I'm gonna give you a simple example. I'm gonna go backwards. For a moment. What if, I'm gonna start with something really simple. I'm gonna start with the following power series. Let's say it's 1 over n, x minus 3 to the nth power. This is what we did today in class. And then we determined the interval of convergence. We did stuff like that. Not a really big deal. Okay? It's not that exciting. I'm going to give you a differential equation. You worked backwards and you figured out that the solution to the differential equation was exactly this. That would be unbelievably powerful and cool, but there's no function that equals that. There is no sine, cosine, e to the x that is equal to that. Remember, of every function that exists, and by the way, we only think of a handful. E to the x, sine x, cos x, and then I can always tweak those, but there's only in fact, in Calc 2, I guarantee you, you did not do more than sine, cosine, inverse, tan, log, and e to the x, and the geometric series. But then what you learned how to do was tweak all of them. But there's an infinite number of I can just generically write anything I want there and it's a power series, but there's no function that it equals. So my point was, if I saw a pattern and I could write the final answer like that, I mean, I'm dancing in the aisles. Because that is so much better than the plus dot, dot, dot. But the chances are probably not great that I'm going to be able to give you a closed form of a final answer. But there's an infinite number of power series that don't equal any specific function. So that's what I'm saying. I don't need you to remember the specifics. But here's the stuff that we did in Calc 2. This is on my next quiz in Calc 2, soon to come up. I remind them this, okay? Oops. Okay, I remind them of this, and then I said, now here's what I'd like you to do. I'd like you to tell me what is e to the negative x squared over x cubed as a power series. Now, you did this by taking several derivatives, evaluating all of them at 0, because this is x minus 0. Evaluating at 0, determining the coefficients. So that means I got to take several derivatives. I don't want to take one. You realize how long? Product rule, quotient rule, chain rules. By the time I'm to my third derivative, I filled up the whole board. Oh my God, that would be a nightmare. Do you all agree? I don't want to do that. I don't need to. Because I show, because the interval of convergence of this is all real numbers. Here's what I teach in Calc 2. This is the most important thing that you learn in Calc 2. I like using formal mathematical language whenever humanly possible. That is the entire point of Taylor series, is once you establish a series for any of the important ones, sine, e, stuff like that. Now if I replace the argument, it's that easy 100% of the time. It's never going to be a time. So does that make this hard or easy? Well, how about if I write it as 1 over x cubed times the sum from n equals 0 to infinity of 1 over n factorial negative x squared to the nth power. Oh. Now what? Well, let's see. Let's bring the index is the only thing that can't be moved. Everything else can be moved in or out. Remember I said the coefficient moves in? That's treated as a coefficient. There's no n on that. So what does this become? Well, what does this become?
Negative x.
So how about negative 1 to the n, x to the,
2x. Oh, minus 3.
I'm done. I've now written a closed form of that function. And one of the things, again, I do in Calc 2, because this is where we do all this stuff, I show you how to take things like this and tell me, most textbooks don't have that one. I give you power series and show you how to work backwards. You're going, you know, that looks very E-ish, or that looks very cosine-ish. And through a little bit of manipulation, sometimes you can work backwards. It's kind of cool stuff, okay? Everybody okay with that? So again, the rules of what you can do with the power series algebraically, you started in Calc 2 but didn't spend a lot of time. I went over a lot of that at the beginning of class today. What you can do, the most important trick, technique, whatever you want to call it, is manipulating the indices so that I can combine different power series together into one power series. We just did it for 2. But what if this problem had a first derivative also? And what if they didn't all line up perfectly? Well, I just take the time and trouble to make everything start at the same place and have the same exponent, and I might have to have a few terms in front of the power series. That's okay. Yeah.
In the big example,
I'm talking about this problem?
Yeah, going from the steps of finding a to n plus 1 to then writing y equals, you kind of erased it over to the left, but the y equals a0 plus.
Well, A0 times. I factored out the, are you talking about the right?
When we actually said y equals.
Oh, okay, that's sort of the generic form, right?
Where'd you,
Where'd I come
how
up with
did you
that?
come up with y equals, and then the following step of.
Well, we're starting by saying, we're assuming at the very beginning of the problem, we're assuming our answer has this form.
Right.
And what is this? This is A0 plus A1x plus A2x squared, and so on. Then what we did was we actually figured out A0 and A1, I don't know what those values are. But every A that came after that, if it was even, was a multiple of A0. If it was odd, was a multiple of A1. That's what we figured out over here. And so then what we do is we rewrite this with all the later terms expressed as multiples of A0 and A1. That's why I could then write 2 different summations, one with an A0 factored out, one with an A1 factored out. But we separated them very specifically odd and even. That's not always the case. Let's suppose we had a problem where we had a second derivative, first derivative, y. And when we did all the manipulation and we did everything we did here, maybe we got something that said an plus 1 equals bunch of stuff times an. In other words, they only differed by 1. Then we would just find A1, A2, A3, A4, A5, and everything would be back in terms of A0, every single term. Then we would hope and pray by the time we got to about the 4th term that we saw a clear and obvious pattern. If we haven't, we probably won't. and then I just write the answer in sort of the ugly form. And by the ugly form, I mean you're actually writing it more like this. Okay? Because there's no clean, closed way. The one we just did, we were able to write summations. That's way preferable. Remember, you're doing stuff on a computer. It's kind of hard to do dot, dot, dot on a computer if I actually want to get a specific answer. Okay? So this is the beginning. Nothing that we did today I want it to be taxing. People always freak a little bit because they're thinking, okay, Calc 2, this stuff challenged me, but have we really used much of Calc 2 today? No, except this is what a power series is. Oh yeah, that's right, we did those way back when. Your ability to set up the problem and manipulate the indices is actually the most important part. I can't teach you how to see a pattern if one isn't clear and obvious. This one, it was clear and obvious. That's why I did this problem to start with. But when you start doing a few problems, you'll say, oh, some of the ones, certainly the ones at the beginning of this section are probably really easy. And then that fades really quickly. And then all of a sudden they're not really easy and obvious. And okay, so I just live with it. And I don't worry about it. Now, what if at the beginning of the problem I said, oh, and y of 0 equals, and y prime of 0 equals, what is y of 0 in this problem? A0. Why? Because it's A0 plus A1x plus A2x squared. So y of 0 has to be A0. And what's y prime of 0 have to be? A1. Because after the first derivative, you just have a A1. So when you're given initial conditions, that usually makes it pretty simple to find those coefficients. I don't need initial conditions in this case. It's not that interesting. Okay? You gonna stop? Okay, now here's what's going on.